All right, so like I said, this is where we left off the other day. And we decided we wanted to try this one by the tabular method and see what happens. So if I'm going to use the tabular method, u is cosine x, and dv is e to the 2x dx. So I start taking derivatives. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Derivative of negative cosine is sine. Derivative of sine is cosine, and at this point we should see that we've looped back. We're not getting anywhere doing it this way. And so right there, doing the tabular method, this should tell you you're looping around on yourself. So it tells you you're going to have one of those infinite loop things. All right, we come over here, we start taking integrals. We get 1/2 e to the 2x, 1/4 e to the 2x, 1/8 e to the 2x, 1/16 e to the 2x, and then plus, minus, plus, minus, plus. All right, so now the deal is, here's our first one. So our first one is cosine x times 1/2 e to the 2x. And our second one would be minus, because we have a minus, but then we have another minus right there, so that's going to make it a plus. And we go like so. Sine x 1/4 e to the 2x. And then, yeah, but when we go to the next row, we've kind of cycled back to the beginning already, haven't we? Because our original problem had a cosine and an e to the 2x. So here we're going to have a cosine and an e to the 2x. The minus sign doesn't bother us. It's repeated. Yeah, so what has to happen at this point, the next one is going to have plus, minus. It's going to have a plus, right? But the next one really should have an integral in it because we cycled around. So it should be the integral of what? Negative cosine x 1/4 e to the 2x. So how come you went straight across that time? How come you didn't go across and sneak down?
Because it's what we were using before based on the...
Because that's right. This would be our du, and this would be our v at that point when you're doing the integral. Okay?
And we pull the negative 1/4 out.
And then we pull the negative 1/4 out, and right, so we have e to the 2x cosine x. And so our trick at this point would be we would pull the negative 1/4 out, and then we added this to both sides, and then we divided. So the tabular method will work.
But you got to be a lot more observant.
You got to be very observant.
I got to look the other way.
I think I do too. I think I just like working out the u and the dv each time and doing it. So the tabular method will work. Once you got used to it and you got good at it, I think it would save you time. But I think you'd have to do a bunch of problems and get very familiar with it before you could do it safely. Okay? Questions on that or anything else? All right, so today we move forward. Section 8.3. Powers of trig. Let's say I asked you to integrate sine cubed x cosine x dx. I'll give you a hint. You can do this one already. This is nothing new. This is a Calc 1 question. You're doing derivative.
You just let you know.
You're doing derivative. Let u be sine of x, because the derivative of sine will give us cosine. So this is a u substitution problem. U equals sine x, and du works out perfectly. That's cosine x dx. So that just becomes integral of u cubed du. And the integral of u cubed is u to the 4 over 4 plus c. So that's 1/4 cosine, u will sine sine to the 4th x plus c. Would it matter if I changed that power from a 3 to a 9? No. Well, then you'd have u to the 9th here, right? But the u substitution would be exactly the same. So this power right here really doesn't matter. What matters is that we had a cosine, so we could make u substitution work. Conversely, what if I gave you this problem? The integral of sine x cosine to the 8th x dx. Again, that's a Calc 1 problem. You can do that one. U is cosine. In this case, u is cosine because the derivative of cosine is going to give you a negative sign. So this one we would have u equals cosine x. Du is minus sine x dx. So this becomes minus the integral u to the 8 du. So that's minus 1/9 u to the 9th plus c. And I plug my cosine back in. Minus 1/9 cosine to the 9th x plus c. So these trigonometric integrals are really easy as long as you have just a cosine or just a sine, because then you can just do u substitution, correct? So what are we going to do in this chapter?
Things that we can't do with u substitution.
Things that aren't quite that easy. So let's say I changed it slightly. Let's say I wrote it as sine squared x cosine cubed x dx. So unfortunately, I don't think u substitution works directly. I've had some people tell me, why don't you let u be cosine cubed? That doesn't quite work. Why not? What's the derivative of cosine cubed? 3
Cosine squared
times sine x. Yeah, it would be 3 cosine squared x times negative sine x. You don't get that sine squared that you need, do you? And by the same way, you could try letting u be sine squared, and you would find it doesn't work. You'll trust me. Thank you. So, what I really wish I had a sine all by itself or a cosine all by itself, so I could just do a u substitution. So I'm going to make it so that I do. I'm going to rewrite this as the integral of sine squared x times cosine squared x times cosine x. So what did I do there? Nothing too fancy. I split it. I took cosine cubed, and I chose to write it as cosine squared times cosine. That doesn't help yet, but now I'm about to fix it. There's a famous identity that involves cosine squared. What's the famous identity that involves cosine squared?
Cosine squared equals 1 minus x.
Very good. It's usually written this way. Sine squared x plus cosine squared x equals 1. But you're absolutely right. I can subtract the sine squared. And that's what I'm going to do. I'm going to write this as sine squared x. And then cosine squared, I'm going to write as 1 minus sine squared x cosine x dx. So now notice what I have. I have a bunch of things with a sine in it. But over here, I got a cosine just hanging out all by itself. And that's very, very useful. What am I going to do next? The other one. U is sine. U is going to be sine.
If you distribute that in, oh yeah, you can do that afterwards.
I can distribute it now or I can distribute it after. That's correct. I'm going to choose to distribute it after.
There's the other theory, sine.
I'm going to do it later because it's less writing. That's exactly right. I'm going to be lazy. But there was the idea. The idea was we wanted to get it so we had a cosine hanging out all by itself, and then everything else with signs in it. Because the derivative of sine will give us cosine. So u equals sine x. du is cosine x dx. So that becomes the integral of u squared times 1 minus u squared du. I distribute, I integrate, plug my x's back in. It's an easy problem now, right? That's u squared minus u to the fourth du. 1/3 u cubed minus 1/5 u to the fifth plus c. 1/3 sine cubed x minus 1/5 cosine cubed x plus c. Oh, how about sine? And how about to the fifth? Yeah, I don't know what the heck I was thinking there. 1/5 sine to the fifth plus c. All right. So we're going to be using identities in this section. Correct. So the important thing here was that one of these two powers was an odd number. Why was it important that this one was odd? Because I can take one out, I can write it as a cosine squared times cosine, I can save one of them. If it was even, it wouldn't work.
I have a question. If you were to rewrite,
Yeah, it would not work. My guess is what you're thinking is maybe you write sine squared as 1 minus cosine squared.
yeah,
That wouldn't help because then my u would be cosine. I wouldn't have a sine hanging out to deal with, would I?
but if you recombine them, then you would only have one trig function, and you would have a subtraction.
Correct, but I would end up with the integral of cosine to the fifth, and I don't know what the integral of cosine to the fifth is. So that doesn't help. All right, so it's important that one of these two powers be odd. Does it matter which one? Not really, but that tells you which one to work with. All right, so let me do another one here. All right, so let's try the integral of sine to the fifth x cosine to the fourth x dx. So I'm going to do it wrong the first time to answer your question. All right, so what you just asked, couldn't I do this? Could I write this as integral sine to the fifth x, and then write this one as cosine squared x cosine squared x? This is wrong. This is not going to work. This is not going to work. Can I do that? Yes, I can. I can do that. And then what am I going to do with cosine squared? 1 minus sine squared. Should I do it for both of them?
It doesn't matter what you get wrong either.
It doesn't matter because it's not going to work either way. Because you're then going to end up with sine to the fifth x, and this would be 1 minus sine squared x. And I'll leave this one alone just for a minute. Cosine squared x dx. It doesn't work now to let u be sine, does it? Because if u is sine, the derivative of sine is cosine, and that's not going to help. On the other hand, if I convert this one, if I write this one as 1 minus sine squared, and I let u be sine, derivative is still cosine, I don't have a cosine anywhere now. So that doesn't do me any good. All right? So what you want to do is you want to look at these, and you want to look for the one with the odd power. So which one has an odd power?
I'm going to guess.
You're going to go with sine. Very good. So sine is the one with the odd power. So what you want to do is you want to pull off one of them. So I'm going to write a sine x. Pull off exactly one. And then left over would be sine to the fourth x.
Now, does that translate to sine squared x
Absolutely, and that's what you're going to do. You're going to come off to the side here a little bit, and you're going to realize that sine to the fourth x is sine squared x squared. Because when you have a power followed by another power, you multiply them. And then sine squared, you're going to write sine squared as 1 minus cosine squared. So this is 1 minus cosine squared x squared. So you're going to come back to your integral now and make that substitution. This is integral sine x, 1 minus cosine squared x squared, cosine to the fourth x dx. So now you have it in a form that'll work. Because now I'm going to let u be cosine, and so I'll put a u there, I'll put a u there, and then the derivative of cosine is going to give me negative sine, but it gives me the sine, which is what I really needed. So u equals cosine x, du is minus sine x dx. So this becomes minus the integral 1 minus u squared squared times u to the fourth du. Yeah, all I have to do now is expand. So I'm going to take 1 minus u squared squared, I'm going to FOIL it out. I'm going to distribute the u to the fourth through.
So it's u to the fourth minus u.
Nope. It's minus. How do I take 1 minus u squared and square it? It's 1 minus 2u squared plus u to the fourth. And then I have to take all that and still multiply it by u to the fourth du. Minus the integral of u to the fourth minus 2u to the sixth plus u to the eighth du. And finally, I have something written in a form that I can integrate. I can just do term by term now. We end up with minus 1/5 u to the fifth minus. I left my minus outside and I put a parenthesis. If you want to distribute your minus through, you can. Minus 2/7 u to the seventh plus 1/9 u to the ninth plus c. And so I think I'll distribute my minus sign through now and plug all my cosines back in. Final answer looks like it's minus 1/5 cosine of the fifth x plus 2/7 cosine of the seventh x minus 1/9 cosine of the ninth x plus c.
Sometimes I wonder why
Integrals are not easy.
Look, it's simplified.
Well, it's a simplified as much as we're going to simplify it. I wouldn't say it's simple, though. So there's a difference. All right. How about the integral of sine cubed x cosine cubed x dx? So when you see these ones with sines and cosines, what you really hope is one of the powers is odd.
If they're both out, you gotta pull one out of each.
In this case, they're both odd. We only got to pull one out of one, and we don't care which one.
Well, yeah, because then we just get.
Which one?
Sine's better because then it's just cosine instead of cosine.
Okay, so you're absolutely right. So eventually, I would prefer to let u equal sine, because the derivative of sine would be cosine. So what that tells me, if I want u to be sine, I want to save the sine cubed, and then the cosine cubed, I want to write that way. So in this case, the reality is you can do it either way. You can pull out one cosine, or you can pull out one sine. You'll get correct answers. The interesting thing is, if you do it this way, all of our answers are going to have sines in it. If you did it the other way, all of your answers would have cosines. But this is the way I would do it. Given the choice, I always pull out one cosine. All right, so this becomes integral sine cubed times 1 minus sine squared times cosine. Because I want u to be sine, du is cosine, and I don't have to worry about keeping track of that negative. So that's my way of doing it. That's my opinion. All right, integral of u cubed times 1 minus u squared du. And that's a pretty easy one from there. That's the integral of u cubed minus u to the 5th du. Looks like our final answer is going to be 1/4 sine to the 4th x minus 1/6 sine to the 6th x plus c. Questions on that?
What do we do when it comes to tangents and secants?
What do we do when it comes to tangents and secants? We'll get to that in a minute. Before we talk about that, what do you do if you don't have odd powers? Give up. No. Just my other class today, they just wanted to cry. Every time I asked them, what do you do? They said cry.
Well, we choose to hold the tutor side.
Right? And then it got even worse, so they decided they just wanted to roll up in a fetal position and throw the blankets over their head and make it all go away. All right, so what do you do if the powers are even? In this case, we have just a sign and the power is even. What you're going to do, if all the powers are even, you're going to use something called the power reduction formulas. So that's another trig identity that you need to know. Power reduction formula. Which one do you need to know? So far you need to know sine squared plus cosine squared equals 1. That's the easy one to remember. All right, anybody remember the power reduction formula? There's one for sine, there's one for cosine.
Do you know how many trig identities you have remembered throughout the years?
Several hundred. There's a lot of them. I agree.
Oh, by the way, there's a new trig function for you.
But here's the important one for you for today. Sine squared x is 1/2 times 1 minus cosine of 2x.
I think I've seen that before.
I'm sure you've seen that before. Why is that called the power reduction formula?
We lost power.
We lost a power. We went from power 2 to power 1. The penalty is you now have a double angle. You have a 2x there. That's the penalty for reducing your power. And there's another formula for cosine squared. We'll need this one here in a minute too. Cosine squared x is 1/2 times 1 plus cosine 2x.
There's hyperbolic ones like that, right?
There are hyperbolic sine and hyperbolic cosine formulas that look very much like that also, yes. You had to use one for one of the homeworks?
Actually, yeah.
Huh. Good.
That one actually had
Yeah.
Okay, so once we know these formulas, we're good to go. So we're going to take sine squared x and we're going to rewrite it using this formula. So that becomes the integral of 1/2 times 1 minus cosine of 2x dx. We reduced the power. I'm going to rewrite that slightly. I'm going to write this as 1/2 integral 1 minus cosine 2x dx. All I did is I pulled that 1/2 out front. And then I can integrate. What's the integral of 1? X. So that's 1/2 times x minus, what's the integral of cosine 2x?
sine 2x plus 2.
You gave me the derivative. The integral of cosine is sine, but because we have a 2x in here, not times 2, that would be derivative. Antiderivative is divide by 2. So this would be 1/2 2x plus c. There's your answer.
The integral
derivative of cosine is negative sine. The integral of cosine is positive sine. But we already had a minus sign in front of it, which is why this one has a minus. Questions on that? Correct. This is really a u substitution. That's exactly right. What you really have to do is u equals 2x. So du is 2 dx. So I need to sneak a 2 in front of here, which means I need to sneak a 1/2 in front there. And that's where the 1/2 comes from. All right. How about the integral of sine squared x cosine squared x dx? Well, the first thing I would do, I would look at that and I would say, crap, I don't have any odd powers. Because these problems are easier when you have an odd power. So in this case, both the powers are even, so what do I do? I do power reduction on both. That's exactly right. All right, so this becomes the integral of 1/2 times 1 minus cosine of 2x times 1/2 times 1 plus cosine 2x dx. Isn't that convenient? Somewhat, as we'll see in a minute. So I'm going to pull the 1/4 out front. And then I'm going to go ahead and I'm going to take these two binomials and I'm going to do FOIL and see what I get. So what do I get when I do FOIL? 1 times 1 is 1. And then the outside ones and the inside ones cancel. So I'm left with minus cosine squared of 2x. Which is sine squared of 2x. That's true, but that doesn't help because that's still an even power. I power reduce again. That's exactly right. All right, so we're going to have 1/4. The integral of 1 minus 1/2 times 1 plus cosine of 4x. Every time you use the power reduction formula, what happens to your angle? It doubles. Every time you use the formula, your angle doubles. dx. All right, so we're almost done here. So I say 1/4, the integral. I'm going to distribute this 1/2 through. I'm going to have 1 minus 1/2, that's 1/2, minus 1/2 cosine 4x dx. That becomes 1/4. The integral of 1/2 is 1/2 x minus 1/2. Okay, it's going to be 1/8 altogether, right? Because when I integrate cosine 4x, I'm going to need a 1/4. Same trick we had on the last problem. It's really a u substitution problem. Sine of 4x. Let's see.
Algebra you did 2 steps up. Yeah.
Here?
Yeah. Here, there to the next step.
There to there?
Yeah.
All right. What I did is I distributed this 1/2 through. So I had 1 minus 1/2.
Okay.
And that's 1/2.
Oh yeah. All right.
And then
I see.
the 1/2 distributed there. So as you can see, sometimes you have to use the power reduction formula more than once. And here's a good example. We had to use it twice. Might you have to use the power reduction formula 3 times?
Oh, probably.
Oh, probably. When would you have to use the power reduction formula 3 times? Let's say this started with something like a cosine to the 6th. You'd have to power reduce 3
Now,
times.
you first, if they were on the 6, you'd break it into 3 separate multiples of the second power. Then you reduce all 3 of them for each one.
And then have to FOIL it all out. And then you'd end up with a cosine to the fourth. You'd end up with a cosine squared and a cosine to the fourth. So you'd have to use it on the cosine squared and the cosine to the fourth. And then you'd have to use it on the cosine to the fourth one yet again because you would get another cosine squared. So you'd actually have to use the power reduction formula 4 times on that one. We're not going to do that problem. But that can happen. So it can happen that you have to use the power reduction formula multiple times.
Why does that hang? Why do you have to double it every time you do it? Double the angle.
That's one of our famous rules from when we took trigonometry, is that sine squared x can be written that way with a cosine 2x.
Yeah, and then I just don't get why the next time you had to do it, you had to do it with a 4x.
Because the next time I did it, I didn't have just an x here, I had a 2x.
Oh, okay.
So x becomes 2x, so when I plug 2 in here, I got 2 times 2x, which is 4x. And so every time you use it, you're going to double your angle.
Okay.
So your angles are going to go 1, 2, 4, 8, 16. Hopefully you never have to use it that many times.
16x.
Correct. All right, so that's sines and cosines.
That's the final answer to that last one.
Absolutely. There's the final answer to that one. Okay. So that was sines and cosines. And somebody asked a minute ago, what do you do if you have tangents and secants? You don't want to know? Too bad. I'm going to tell you anyway. What's that? Oh, I got some in there I don't need. All right. How about the integral of tangent cubed x, secant squared x, dx? Any suggestions?
Well, we know that secant squared x is
So what you're telling me is this one's an easy one. U equals tangent x, because the derivative of tangent turns out to be secant squared. All right, so this just becomes integral of u cubed du. So that's going to be 1/4 tangent to the 4th x plus c. All right, so here's the general rule. The first general rule with these is you want to look for secant with an even power. Secant with an even power is a very good thing for tangents and secants. So why is that? What if I change this problem slightly and I make it tangent cubed x, secant to the 4th x? So I look at that one and I see good news. The good news is I have an even power of secant. Why is that good news? I'm going to break it. So I'm going to write this as tangent cubed x times secant squared x times secant squared x dx. And eventually what I want to do is I want to say u equals tangent, because the derivative of tangent will give me secant squared, but I've got another secant squared. What am I going to do with that other secant squared? Get my bottle of white out, erase it, I didn't need it. No. There certainly is. Everybody remembers this one. Everybody remembers sine squared plus cosine squared equals 1. Close. Take everything here and divide it by cosine squared. What's sine squared divided by cosine squared? Tangent squared. What's cosine squared divided by cosine squared? 1. And that one equals secant squared. So what am I going to do with this other secant squared? I'm going to replace it by tangent squared plus 1. Right, so that's how I remember these. I always remember this theorem, sine squared plus cosine squared equals 1. If I need one of the other ones, I figure it out by dividing. That way I only have to remember one thing. Okay? The good news is you don't have to remember any of them. Why not? Because you get an index card, and if I were you, I would highly recommend you write these things down on your index card.
That's what I would finally relate to. We have so much stuff.
You think you got a lot now, wait till we get to chapter 9.
It's
It's going to get a lot worse. All right. So anyway,
He's like, why does he laugh at us like that when he says it?
because I know what's coming. I've seen it before. All right. So anyway, the key is if you have an even power of secant, life is good. If you have an even power of secant, you're going to pull out a secant squared, and all the other secants that are left, you're going to use your identity to get rid of them and write them using tangents. And then u becomes tangent x, and du is secant squared x dx. Works out really well. We end up with u cubed times u squared plus 1 du. All right, so that's the integral of u to the 5th plus u cubed du. 1/6 u to the 6th plus 1/4 u to the 4th plus c. Plug my tangent back in. 1/6 tangent to the 6th x plus 1/4 tangent to the 4th x plus c. Questions on that one? All right. Let's change the problem slightly. Integral of tangent cubed x, secant cubed x, dx. So when I look at these problems with tangents and secants, the first thing I always look for is I want secant to be even. Secant have an even power? No. Rats. I could take one out. I could write it as secant times secant squared, but that's not going to help because the derivative of tangent is secant squared. I need that secant squared to survive, and it's not going to. Other good ideas? All right, well, let's think of it the other way. If u were to be secant, what's the derivative of secant? Secant tangent. So, could I, if I'm going to let u be secant, could I save a secant tangent? I think I could if I write this as tangent squared x, secant squared x, times secant x tangent x. So what did I do there? I pulled out both a secant and a tangent, didn't I? All right. So here's your rules with secants and tangents. First, you look for secant to be even. If secant is not even, you need tangent to be odd. And if tangent is odd, you're going to pull out one secant and pull out one tangent. And how's that going to help? What are you going to do with this tangent squared over here? You're going to use your Pythagorean theorem to change that to a secant squared. Correct. All right, so let's go back and look at our Pythagorean theorem again. What's secant squared? Let's see. Tangent squared would be secant squared minus 1. All right, so that's the substitution we're going to make. So tangent squared, this tangent squared right here, that becomes secant squared minus 1. And then I have this secant squared, and then a secant and a tangent. So u is secant, and du works out perfectly. It's the secant tangent that we saved. All right, so we have integral u squared minus 1 times u squared du. From there, it's easy. Integral of u to the 4th minus u squared du. 1/5 secant to the 5th x minus 1/3 secant cubed x. Let's see. All right, so little summary here. If I give you sines and cosines, what do you look for? Nope. When you see an even power, that's when you get mad. You look for an odd power. Let's say, just for argument in this case, n is odd. What are you going to do if n is odd? You're going to write this as cosine m cubed, and you're going to take 1 away from there, right? And leave 1 out here. And then you're going to convert this one. Not power reduction, because this is now going to have an even power. So now we can use our sine squared plus cosine squared equals 1. So with sines and cosines, that's what you really want to look for. You really want to look for one of these two letters being odd. It really doesn't matter which one. As long as one of them is odd, you're pretty good. If neither of these numbers is odd, power reduction. Both m and even, that's when you have to use your power reduction. And in my opinion, those are the harder ones. You think they're all? Well, I didn't say any of them were easy. I said these were harder. It's levels of difficulty. All right, and then with tangents and secants. Tangents and secants are a little bit harder to remember. Two possibilities. If n is even, then what are you going to do? U is going to be tangent, which will make du secant squared x dx. So if n is even, you want to save a secant squared and then convert the other ones. So if n is even, save a secant squared, convert the rest of the secants. Using the Pythagorean identity, correct. Pythagorean identity. Your other possibility is m is odd. All right, so this is why I think the sines and cosines are easier to remember. The sines and cosines, you want one of them to be odd, it doesn't matter which one. If one of them's odd, you're going to use your Pythagorean identities. If both are even, you use your power reduction identities. There's less to remember. For this one, you either want secant to have an even power or m to have an odd power. And if m is odd, then you're going to let u be secant x, and du is secant x tangent x dx. So you, in this case, you want to save a secant x tangent x, and convert the rest of the tangents to secant squareds. I think that one's a little harder to remember.
So what happens when the secant is odd?
What happens? That's a great question. I was hoping somebody would ask that. What happens when neither of these work?
Is there a power reduction?
There is not a power reduction. If neither of these work, one of two options, generally. Wolfram alpha, three options. Three options. Option 3 is Wolfram alpha. Of course, that's not going to help you on the test. Option 1, convert everything to sines and cosines and see what you can do. That'll work most of the time. Option number 2, integration by parts. Because you do have multiplication here, don't you? So you could try integration by parts. When you do integration by parts, in general, what are you going to have to be who? What's going to be u and what's going to be dv? Well, you have to think about what you can integrate. You can integrate secant, but what do you get when you integrate secant? No, that's a derivative of secant. What's the integral of secant?
No, when we do the integral tangent becomes natural log.
The integral of secant turned out to be natural log of secant plus tangent. So in general, you do not want that to be your dv. That would be bad. You also do not want dv to be tangent. What's the integral of tangent? Natural log of secant. Again, that would be bad.
So what do we use? Yes.
Good things to use for dv would be secant squared, because you know the integral of secant squared.
Oh, that's right, we do know.
Another good thing for dv would be secant x times tangent x, because you know the integral of secant x times tangent x is secant x. Okay?
So there might be ways that we can manipulate it.
Correct.
Actually,
So we will do one of those next time. If I forget, remind me that I want to start with that one. So that's one that does not fit one of our patterns, does it? Because the secant has an odd power,
You're being nice to it for a tangent.
and there's no tangent at all. So that's one that does not fit either of these two, and this is a famous integration by parts problem. So we'll start with that one next time.